algebra. When we come to set algebra, remember we should be able to define what is a set, right? Remember this year we're talking about some collection of ordered objects or some collection of objects which are defined. We can talk about definite objects, right? Which are an element of a certain set, can be integers or real numbers, any of that. So we must know what is a set, the properties of a set, and how do we treat a set, right? So first, when we look at this, first they say that on theorem 3.3.2, they say that we should let A, B, C be sets. And then A and an empty set is equals to an empty set. I'm sure for now we know what is an empty set, right? Say that A and an empty set is equals to an empty set. And we know what is this sign for an intersection, right? So now we say that also if we take A and A, or A intersect A, we're still going to get A. Or if we take a set intersected with itself, we're still going to get that set. Then if we say A and B, we can apply commutative. So here we're going to be looking at some laws, the logic laws which we discussed in chapter 2, logic mathematics, right? We're going to be looking at those laws. So when it comes to those laws, we spoke of idempotent. Idempotent, let me say, okay, before I start with idempotent, let me start with domination law. We spoke of domination law. Domination law says that when I'm comparing a statement with a truth value, I'm going to get that the answer will be that truth value. Is that right? Let's say I take P, compare it with 0. If I get 0, it means that this is domination law. The truth value is dominant. Since here we talk about truth values, right? Now, from this part, we are going to say that this we're going to apply domination law on the first part. We're going to be applying domination law here. Here, we are going to be applying idempotent. We know idempotent. Usually we spoke of it to say that if I take a statement with itself, I'm going to get that statement. You say, right? So this one is idempotent. As long as you're comparing a statement to itself, you are going to get idempotent. I'm sure we see this. Now, let's say now I'm going to be shifting statements. Let's say I have A and B, then I shift them of their positions. That is called commutative law. You see that if I shift statements of their positions, it's called commutative law. And if instead of shifting statements, I just shift brackets, now it's called associative law, because I'm now associating between the sets. You see, right? Now, besides having all that, what we're gonna be looking at the most is the part of set theory. So first thing that I want us to do is to define a set, right? So I would like to ask you guys what is a set, or anyone to give a definition of a set. But then we know that a set, yeah, we can say that this one, I say that is an unordered collection. It doesn't have to be ordered, right? This one can be an ordered. Now, this set, remember from predicates we spoke about some objects, right? Which those objects are X, Y, Z. You see, right? So we're going to say that a set is an unordered collection of well-defined objects. You see, right? They are well-defined. So I will sometimes look at for all, for some, and so on, right? Well-defined objects. These objects, you'll see when we come to assume, let's say we let, or maybe we let X be an arbitrary element. So this is taken from a set. We know that a set, when we say that this is an unordered collection of some objects, we're saying that those objects are called elements of the set. All the objects that are found within the sets, you see, right? Or let's say maybe we have A. This A contains x, 1, 0, y. This x is an element of A, 1 is an element of A, 0 is an element of A, and also y is an element of A. These are an ordered collection of well-defined objects, right? So they don't have to be ordered. They can be in any form, in any order. I can even have 2x inside here. That's how we say that these are an ordered collection, right, of sets. So since we know, once we start knowing the definition of a set, we can easily come and look at this. We know that this is what? This is an empty set. Which is also the same thing as this. This is the same thing, right? That is the same thing. Is an empty set. Now remember, I said that this law is called a domination law. So if you get time, I'm going to send those laws. If you get time, please try to make sure you know these laws by heart. It's a good approach. Then this one, we know that it is called idempotent. As long as you're comparing same statements, it's idempotent law. This one is the most used. It's called commutative law. These two, the ones below, are the most used. This one is associative. So these two are the most used, right? Associative law. So now we are going to prove. I'm going to show you this. There are different types of ways to prove a set. So the first question here that we're given. Okay, let me say this. When proving a set, right, you can be given the following. Let me say when they are equal, or maybe when A is a subset of B. So here, the aim here, let me say, the aim is to pick an element or an object, to pick X to be an element of A, then we show that X is also found in B. You see, right? Then show, let me just write the full statement, that X is an element of B. So this is what we do when we are proving that X is a subset of B, right? Now, we first pick an element from where, you see this thing is facing this side. So we're going to pick an element from where it is coming from, to show that if this element is contained within this set, it means that it is also contained within this set. You see, right? And this one has more elements than this one. It's either they have equal elements or this one has more. You see, that's why we come to talk about the cardinality, but we'll come back to that. Now, another one is when we have A being equals to B. If I'm given that A is equal to B here, you must know this. You must show that A is a subset of B and B is a subset of A. You see, right? This is what I've already spoken about there. Here, we are going to pick X to be an element of B, then show that X is an element of A, which is what we'll be doing at the moment, right? And we'll be using some of the methods. So for now, let me also define these ones. I'll define these last two. Let me say A, maybe I can define 3. It will depend. Let's say we have A implies B. Here, let me say that the aim is to assume A and prove B. You see, B sometimes can be looking like this, or sometimes it can be looking like this. You'll see when we come to the one. That's why I'm saying that this one will discuss it. But when you come inside here, we must keep in mind that this is the hypothesis and this is the conclusion. You say right now, we always assume this, then deduce this. We have seen something like this. It's not our first time seeing such words, right? We have to assume this, just like we did in set theory and methods of proofs. When we were assuming the hypothesis or the first part, then we deduce the other part. We use the other part to prove that something is correct or is true, right? Then we have this one. A doubly implies P. Double implies B, right? So here I'm just gonna say that this one, I'm just gonna give it to you as a task. Go check what does this one mean, but then we're going to do it in our next session, right? Now we also have these A cross B. The aim here, usually it can happen, let's say A cross B is a subset of B cross A. Here the aim, now we're into this space, right? Across determines the space we're in. The aim is to pick, we're going to pick a pair now, X, Y, being an element of a certain, let's say in this case, let me pick A, B. I wanted to say a certain set, but here this will be the set that we're given. So we pick the left hand side, and then show that, now we must show that also this XY is found in B cross A in the other side. You see, right? So for now, this is what we'll be doing. Once we know all these guys, it will be simple for us to compute. But for now, if we also know that A minus B is equals to, let's say, A and B complement. This one is the same thing as letting X be an element of A minus B and show that X is an element of A and B complement. We'll discuss this in detail, right? Now, let's prove the first one using the context that I was showing you. We have A and an empty set, which is equals to an empty set. So I want to prove this. If we want to prove this one, they say that we must show that A and an empty set is equals to an empty set. You see, right? So for us to prove this, we're going to come here and say this. I'm going to write solutions, or instead of solutions, usually here we say proof, right? We say proof, just like in mathematical induction. Then remember, the aim here is to show that A and an empty set is a subset of an empty set, and also to show that an empty set is a subset of A and an empty set. So when they're equal, you're going to show that this is a subset of this one, and also this is a subset of this one. You see, right? And then let's start with this one. We always start with the one that has a lot of information. So we're going to let arbitrarily, we let X, we pick one element because there's no cross. If there was a cross, we're going to pick two elements, right? But in an ordered pair. But since there's no cross, we're just going to pick X to be an element of A in an empty set. After this, now we expand. X will be an element of A. When you expand, guys, when you distribute this X element of, the sign will be interpreted in words. You see, right? Now we're going to have and. We're going to have and X is an element of an empty set. You see, right? Now, since we have this, we can come now and say that since we have this, what law can we apply? Remember, now I was able to do this, right? And I got stuck after expanding. The question is, what can we do next? Now you're going to apply a law. When you get stuck, that's why it's very important for us to know these laws, right? When you get stuck, you need to apply a law. The law that we're going to apply here, it's called idempotent law. No, not idempotent, man. It's called domination law, right? So we're going to say this. We are going to say that by domination law, we know that if I take a statement and an empty set, I'm going to get an empty set. So it means that this one is going to give me what? An empty set. You see, right? then this is going to give me an empty set. Now, here's how you conclude. Always, you're going to say where you started will be a subset of where you ended. Is that right? So I'm going to say hence A and an empty set is a subset of an empty set. Now, I do conversely, I let X to be an element. Now I'm going to prove the other way around. You say right now, I let X to be an element of an empty set. Now let me give you a trick from this one. If you did this side, guys, these ones of equal sign, they're very simple. If you did this side going to the right, what you just have to do here, going back, you just have to copy these steps going back. You say, right, already we have this one, which is this. It means that the next one is this one, right? So I'm just going to say X an element of A and X an element of an empty set. You say, right. And then from here, I'm going to factor out. Obviously, now I come to this step. You say, right. Now I factor out X, A, and an empty set. You say, right. Now, when I have this, I've already arrived to the solution. Now I can say, hence, this is a subset of this. You say, right. Hence, an empty set is a subset of A and an empty set. So it is simple to prove these things as long as you're able to prove one side. Then you can just copy the steps going back. You say, right. You see that. Now, since we have that this is a subset of this, they are a subset of each other, we can now come and say, thus, according to the question, we're supposed to prove that A and an empty set is equal to an empty set. I'm sure we see this, right? Now we're able to prove that A and an empty set is equal to an empty set. Now let's come to B. If you have any question, please, you can stop me and ask. On the comment section, I can't see anything if you comment there. The second one that we had to check there was A and A is equal to an A. Meaning we know already that we are supposed to prove that A and A is a subset of A, and also show that A is a subset of A and A. Yes? No one unmuted their mics. I think someone unmuted their mic. If you want to ask a question, you can ask it. So, now let's start by showing this one. This one is the simplest. After showing this, guys, it will be simple for us to show this. We just have to copy the steps back, right? It will be simple. Now, we come and do this. We say proof. We let X be an element of this one, right? Be an element of A and A. Then we imply we distribute our arbitrary element. Then this one changes to weight. X is an element of A. Now, what will happen here is that now I'm going to apply law. When I get stuck, I'm going to apply law. I know that when I'm multiplying or when I'm applying intersection of the same element, I'm going to get that element. You see, right? It means that this one is going to be X element of A. Hence, I've proven this. So I'm going to say, hence, A and A is a subset of A. Then I come and say conversely. When I come to conversely, I'm going to let X be an element of, now I prove this one, let X be an element of A. Remember I said that I'm just copying the steps going back, right? Then this would be simple to prove. X an element of A and X an element of A. Then I write this one. I mean, in other words, I'm factoring out X arbitrary element, right? X element of A and A. You say, right? Now, after getting this, we know already that we have proven, in this case, we have proven that this is a subset of this, right? So I can say hence A is a subset of A and A. Now since I've proven both sides, I can say thus A and A is equal to A. You say right? Then I've concluded. Now we say that it is simple for us to prove this, right? Now let's try to say now, okay, we're proving using AND. Why don't we use OR? Let's prove this one using OR. You say right? Let's prove this one using OR. We come to C. C, we say we have A. It's A union B, which is equal to B union A. I'm sure you see this. And remember, the aim here is to prove that A union B is a subset of B union A, and also prove that B union A is a subset of A union B. So let's start with this one, right? We always start with the first one. Proof. We let X be an element of A union B. Then when we expand, we are going to say or X element of B, right? Because that is the sign which is interpreted as or. Then from here we get stuck. Remember I said that this is idempotent. You're going to shift the statements. Already you know what you want. You want B or A. And the only way you can get that is if here you have X element of B, and then here you have X element of A. Then you just shift statements, right? You applied commutative, right? Then I factor out an arbitrary element. Then this will be B union A. I factored out this. If you factor out both sides, the sign is also going to change back. You see, right? Now, this sign will never change. Let me tell you this condition. This sign will never change as long as this is here. You see, right? It must be removed for the sign to change. Now, we have proven that this is a subset of this. Then we say, hence, A union B is a subset of B union A. Then we come and say conversely, we let, now we are proving this one, right? We let X be an element of B or A. Then remember here I said that you are just copying the steps going back. But even if you didn't want to copy the steps going back, you realize that if I expand this, I'm going to get B or X element of A. Then I get stuck here. I need to apply commutative law. I interchange this. If we go back, we'll realize that the steps are the same. When I copy them going back, right? Then I factor out arbitrary element. Then I'm going to have A union B. You see, if we go back, this step is this one. This is this one. This is this. This is this. You're just copying them going back. You see right now? This one was moving going down. This one is moving going up. You're just copying the steps. You see right? And then we say hence we have proven here that B or A is a subset of A or B. Since we have proven both, we can just come and say thus, according to the question, we're supposed to show that A or B is equal to B or A. Then we have proven that question, right? Now we come to the one of intersection. The intersection, let's also do the intersection of OR, right? Yeah, let's do the intersection. But for now, let's do this one of AND. It's fine. We can do the intersection of AND. The next time when we meet, we can do the one of OR. Likely the one of OR is there in the guide, right? So, we are here D. We are given that A and B is equal to, or A and B and C is equal to A and B and C. I just shifted brackets there. Here we know the idea is to show that this is a subset of this and also that this one is a subset of that, right? So I'm going to write proof. Then I let X to be an element of the first one. A and B and C. Then I expand. When I expand, well, there are some things inside the brackets. I'm just going to keep them as they are for now. Then I interpret the one outside. You see, right? Then now I come to interpret the one inside. X an element of A, and X is an element of B, and X is an element of C. Now from here, I just cross multiply, right? Or instead of cross multiplying, even if I was not to cross multiply, let's check the final solution, because sometimes cross multiplying might not give us the final solution, right? Let's check the final solution. The final solution is that we are only just going to shift brackets, so we can just apply such a law here. We only shift brackets. You say, right, I only shift brackets instead of cross multiplying. So because we see that cross multiplying will not help us here. So I say X element of A, and now I factor out an arbitrary element here. I'm going to be left with B or C. Then this will imply that now I factor out these two. I have to factor, first I factor out this one, right? I get this. The next, I'm going to have to factor out these two. You say, right, then I factor it out. This is end. It's not O, man, it's end here. It's end, B and C. We see that right now. So we have shown that this is a subset of this, right? Then we say hence A and B and C is a subset of A and B and C. Now to do the conversely part, remember I said that the conversely part is simple. We're going to we start here. We let X be an element of A and B and C. Remember I said that if you don't want to think too much, you're just gonna copy the steps going back, all right, with this method. So it means that if I copy this one, I'm just going to have, if I apply the steps here, I'm just going to have X element of A and X element of B and C. First I said that I'm going to keep this one and focus on the one outside. Then now I get inside, right? I'm going to have X element of A and X element of B and X element of C. Then I shift brackets. If you check here, this step is this one, this is this one, this is this one, and this one is this one now. It means that now I just have to factor out X element of the X element of, you see right now, which is going to take me to this step. You see, right, let's do that and see. If I factor it out, we're going to have X element of A and B and X element of C. You see, it's the same step as this one. And then from here, I factor out the two that I see here, arbitrary element, X element of A and B and C. Then I say, hence, here, check this. I've shown that this is a subset of this one. You say, right, I've shown that A and B and C is a subset of A and B and C. Since I've shown both, I'm going to say thus A and B and C is equals to A and B and C. I'm sure we see this, right? Then since I've shown both, I'm just going to say that. Now, if we check, these ones are a bit simple. We won't dwell too much on them, right? We won't dwell too much on them. So if you have any question, you can ask, or we can move to the second one, right? But then when we meet again, we're going to do the one of O here. I'm only interested in that one because we're going to be using a different method. So we come to these ones now. Now these ones, they're going to be using a distributive law, because we're going to, the signs are different. Here it's when the signs are different, I distribute A and B, A and C, then the sign here will come in between. You see, right? These ones are a bit simple also. So for A, we are going to prove. For us to prove A, we're going to let first X be an element of this one. Remember, we must show that they are a subset of each other. This is a subset of this, and this is a subset of this one, right? Now, I'm going to let X an element of A and B union C. Then I expand X element of A, distribute now, and X element of, I keep the brackets, it's very important. Then I expand inside the brackets. And then I get inside X element of B or X element of C. Now, since the signs are different, I can't, since these signs are different, I can't shift brackets. I just have to distribute, right? Then when I distribute, I get X element of A and X element of B. Then this all will be outside, since it was inside at the beginning, right? X element of A and X element of C. So when you distribute, guys, the one which was outside will come inside. You see, the one which was inside will go outside. It's always the case. You must keep that in mind so that you don't make such mistakes of swapping the signs. So now I've distributed. Now I can factor out, right, the arbitrary element in both sides. We're going to have A and B, or X element of A and C. Then I factor out the arbitrary element A and B union A and C. Let's see, we got that. You see, right? Then we say, hence, we've shown that this is a subset of this one, right? Hence A and B union C is a subset of A and B union A and C. For now, guys, don't use things like biconditional. For now, here you're not allowed to use them. I'll tell you when is it that you're supposed to use them, but you're gonna use them when we're dealing with De Morgan's law, or you'll see, I'll tell you such laws, or double negation law, right? So now I want to prove the other way around. We're going to say conversely, we're going to let this, again, now we're trying to prove that this is a subset of this one, right? So we're going to just say it's simple when you copy, right? We're going to let X be an element of A and B union A and C. Then I just copy this one. Simple when you copy, guys. I can even do this to show you that I can even say this. If we check, let me copy this one. Can even show you that it is might simple to copy. Just gonna move and copy like that. You see, right now I know that I've copied this one. If I wanted, after this one, I know that I'm supposed to distribute inside. I was going to copy this and so on. I copy while going back. You see, right now. So that is what I was going to do. So let's just do it. We write it down here. Then we expand inside here X element of A and X element of B. Or we expand here X element of A and X element of C. If we check wherever common factor here, we can factor it out, right? We have X element of A, or maybe instead of saying or, we can, you must always know, right? Let me not, I wanted to say X element of A or X element of A. That one will take time. I can just do this. I can say this, it goes with its sign. The sign which is in front of it. It will always go with the sign which is in front. Then it's going to be and here. Then this one will go with this sign. X element of B, or this one which is left in the side, X element of C. But if you were just copying, guys, you were not going to think about it. Since we are here, right? Then we just copy this step. We're not going to even think about such, what is it that we're supposed to do, right? We're just going to just copy like that. Then from here, I factor out arbitrary element here. X element of A and X element of B union C. Then I factor out this one. B union C. Then here, I've shown that this is a subset of this, right? I can just come and say hence A and B union A and C is a subset of A and B union C. Then I say that, since I've shown both, I say thus A and B union C is equal to A and B union A and C. You see, right? Then we've proven that. Now what I'm going to do here, I'm just going to leave this one to say try. This one we've done it. Let me also come back to these ones. And I say try. This one we've done it, we've done this, we've done this. Right? And then if no question also, it means that we can proceed, right? Now if you check, these are simple, guys. They're all simple. You just have to follow through, and if you get stuck, go back and copy, right? And now let's come to this. So we have this now, right? They say if we have the proposition 3.3.5, let A, B be set, then A complement outside complement is equal to A. This law here that they used here, this one we must know that this one is double negation law. We negated twice, you see, negate, negation law, double negation law. And then this one is if-then statement. Let's leave that for now. But we're going to prove it here. Then this one is De Morgan's law. So this one you'll try it. I'm going to prove this. Going to prove this. I prove this, I also prove this. You see, right? Then let's look at the first one. The first one, we're given this A. We're going to prove, right? We remember with A we're given that, okay, let me just write we're given A complement is equal to A. Remember here the aim is to show that A complement is a subset of A, and also show that A is a subset of A complement. As long as there's an equal sign, we're supposed to show this too, right? But since we're dealing with double negation, remember guys, I said that when you're dealing with De Morgan's law and double negation law, you're just going to come and do this. Proof, you let, as long as here it's equal, right? You're going to let X be an element of this one, which is A complement. Then I'm going to double imply. As long as you're dealing with the De Morgan's law or double negation law and there's an equal sign there. You see, right? Going to double imply. This one can be dropped here. When I drop the complement, guys, it's going to be like this. X not element of A complement. Then when I drop this again, it's going to cancel that complement. Then it's just going to be X element of A. And here, since I've used double negation, guys, it is simple for us to come and say this and deduce and say, we're going to say that hence A complement is a subset of A, and so we have proven both same time, right? Is a subset of A complement. Thus A complement is equal to A. You see, right? So this one is simple to do that because we're dealing with double negation law. So it is simple for us to just use double implication here, and then we have proven both sides. Then if we come to B, they say if A is a subset of B, if A is a subset of B, then B complement is a subset of A complement. So what you do here, guys, let me show you. You're going to assume this. You let X be an element of this, then show that X is an element of A complement. You see, right? So we're going to do that. Let's do that. The reason why I assume in something, when you assume it, it means that you're going to use it along the way, right? First, you assume. If you don't assume here, guys, well, you know that there's a hypothesis here. You always assume anything that is in between if and then. If you don't assume it, it will give you a wrong, right? Meaning that you're going to lose all the marks. Assume A being a subset of B, then you let X be an element of B complement. So what we were planning to do here, we're planning to use this thing to arrive to A complement. And we can't use it here because we don't have a B. So we must change this to a B, right? So for us to change that, we're going to say implies X not complement, because I'm taking this here. You see right now, of B. And since this is a subset of B, it means that if X is not in A, it will also not be in B. So that's what we're going to be saying here. So this will imply that X is also not in A. If X is not in B, this will also not be found there, because all the elements of this one are in A. You see right now. Then you give a reason. Since A is a subset of B. You see right. Now, we say now that if I take out that complement, then I put it on top, I'm going to have this. And the aim was to show that if B is a subset of A, if we have B complement, then it will be a subset of A complement. So in other words, we're supposed to take, I should have put a complement here. You're supposed to let X be an element of a B complement, show that it's also found in A. And we have shown, we see that also X is found in A complement, right? Then we say hence B complement is a subset of A complement. Then we are done with this one. You say right. It was that simple. For this one, it's a different story. I'll try to gather more questions based on this. Then we see how can we understand it better. Now let's look at C. C, I say that we're going to be looking at A union B complement, which should be equal to A complement and B complement. I think they use this type of complement here. Yeah, remember this and this are the same thing. They all mean complement. So don't be shocked when they didn't use the same one there right now. Then also here we use C. So since we're dealing with De Morgan's law here, guys, when I'm going to prove, I'm going to do the same thing as long as there's an equal sign here, right? The aim is to show that this is a subset of this, and also this one is a subset of this one, right? Then I'm first going to let X be an element of this. Let X be an element of A union B complement. Then I use double implication, because here I'm dealing with De Morgan's law, and we have an equal sign, right? Then here we're going to drop this complement. Remember, I've shown you that you can drop the complement here. You have this. Then you continue. When you now distribute X not an element of, this is all, right? But when you interpret it, you're going to interpret it as AND, because now it's been complemented. Because you see, X not an element of X not an element of B. Then I take these complements to the exponent. We're using this one, right? Then I factor out X element of. You see, right? Then I got this. Now here, I've shown that A union B complement is a subset of A complement and B complement, and that A complement and B complement is a subset of A union B complement. Then I say thus, since I've shown both, I say thus A union B complement is equals to A complement and B complement. Then I'm done proving this one. Alright, if we check, we're done proving that. Now, what you're going to do yourself, you're going to prove D. Try D. Alright, you're going to try D, and then we'll take it from there, right? Now let's see now. And this one we've already done it. This one is a tutorial. So let me put the tutorial somewhere here. Let me say try this, right? Because we've already proven something similar to that. And then after trying that one, I want you to try this. You try this tutorial. Yeah, I want you to try these three, right? So it means that, yeah, I think we can end the session here. The rest we're going to do them when we have the next session. Yeah, for now, let me end here, not to make the recording to be very long. Let me just stop it here, and then I'll send these things to you guys, also the recording.